The next topic in Chapter 8 is oxymercuration demurcuration, and this is an alternative to acid-catalyzed hydration, except with this type of reaction we don't get rearrangements. So we still get Markovnikov addition of H and OH across a double bond, but just avoiding rearrangements. Okay, so with oxymercuration demurcuration, we could do a reaction like this. So here we have propene. We're going to add something across the double bond where the OH goes to the more substituted side, and then in the product we end up with what was essentially adding H and OH across the double bond. So it's called oxymercuration demurcuration because we get this mercuric acetate species added to the less substituted side, then the mercury is removed and replaced with a hydrogen. So that's why it's called demurcuration. So to form our mercury reagent, mercuric acetate is used. Okay, and this is acting as a Lewis acid catalyst in this reaction. So in the first step of the formation of the reagent, the mercuric acetate breaks down where one of the acetate groups leaves, leaving us with a mercuric cation. And the acetate is just like the conjugate base of acetic acid. Okay, so this is the acetate anion here. Okay, so we can compare the oxymercuration with the formation of a carbocation. So that would be an alternate reaction wherein just the acid-catalyzed hydration, in the first step we protonate the alkene, getting a carbocation, and the hydrogen goes to the less substituted side. For oxymercuration demurcuration, we're not protonating, but notice that this mercuric acetate species that's formed when one of the acetate groups leaves has a positive charge, but it also has this lone pair, and that's peculiar. So because it has a positive charge, it's subject to nucleophilic attack from the alkene. Okay, the alkene is acting as a nucleophile, which will attack the mercury because it has that positive charge. But then the lone pair from the positive charge will attack the newly formed carbocation. So it isn't really, a carbocation never really forms here. This is a concerted mechanism whereby the alkene acts as a nucleophile attacking the mercury, and as the positive charge builds up on the more substituted side, the lone pair from the mercury then attacks that positive charge in a second nucleophilic attack, forming this bridged mercurinium ion, which is a three-membered ring. These mercurinium ions don't rearrange, and because this is essentially a concerted mechanism, the formation of this mercurinium ion, we don't get rearrangements through the formation of this cationic species either. So they won't rearrange after they're formed, and they don't rearrange as they're formed. Okay, but they aren't exactly symmetrical. The mercurinium ion that is formed in this intermediate actually will be primarily located on the less substituted side of the alkene, because the alkene, the side that has more alkyl groups, will be able to better stabilize the positive charge from that species. So these alkyl groups will actually, where are we at here? So the alkyl groups, remember, are electron donating, and they're donating electron density N, which stabilizes the positive charge of the mercurinium ion, which essentially elongates and weakens the bond from that side of the alkene, what was the alkene, to the mercury. So that's essentially giving that side, the side that's more substituted, more carbocation character. And because it has more positive charge character, it's going to be more subject to nucleophilic attack. So the nucleophile attacks the more substituted side of what was the alkene. So we still get Markovnikov addition of the nucleophile to the more substituted side of the alkene. Now the mercuric acetate species goes to the less substituted side. Now in the final step of this reaction, sodium borohydride is used to remove the mercury and replace it with a hydrogen. And this goes through a free radical mechanism that we don't discuss in this course. So the overall reaction is mercuric acetate and water, which is our nucleophile, in the first step. In the second step, we have sodium borohydride, and for most professors, it's perfectly fine to write all of this together over the reaction arrow and not separate that out by steps. I would expect my students to mainly give me, the top portion here. If they can remember that, I'm happy. But many professors would expect you to write the entire reaction, okay? So we have this entire reaction giving us essentially H and OH added across the double bond of the alkene. Alright, and so if we had done this reaction with acid catalyzed hydration, we would have added H and OH across the alkene, but it would have been subject to rearrangement, which would have occurred from a shift, a rearrangement, when the carbocation formed. Okay, so if we formed a carbocation here, then we would have gotten a hydride shift. We have different starting materials here. That's why I was getting confused. We would have gotten a hydride shift here, okay, that would have resulted in a positive charge over here where the nucleophile would have attacked, okay. Alright, so let's see if we can predict the product for each of these reactions. And if an acid catalyzed hydration had been performed instead, what would have happened? Okay, so let's rewrite this A. Okay, so we've got 6-membered ring, but our double bond is over here. And in the so let's just go ahead and draw the products of oxymercuration demurcuration. Alright, so what are we adding and where are we adding it? We're adding H and OH across the double bond in Markovnikov fashion. Okay. So OH goes to the more substituted side and the H went to the less substituted side, and I just won't show that here. Now if we'd had acid catalyzed hydration, let's go ahead and draw the carbocation that we would have formed in the first step. The carbocation would have been here, and that would have been subject to a rearrangement or a methyl shift to produce a tertiary carbocation. Okay, and then that would have gotten the OH, and then water would have attacked, and then hydrogen removed. So I'll just draw 2 arrows here to indicate there were actually 2 steps. And this would have been the product. So oxymercuration demurcuration, even though we're using toxic and difficult to dispose of mercury, would have avoided that methyl shift. So for B, so that's why we would use acid catalyzed hydration if we can, because it's cheaper, easier, and more eco-friendly. So for B, okay, what are we adding and where are we adding it? We're adding H and OH in Markovnikov fashion across the double bond. So that means we're going to get the, why did I do that? the OH here, and the H would have been on the less substituted side. Alright, and if we had gone through if we'd used acid-catalyzed hydration, we would have gone through a carbocation intermediate. The carbocation would have ended up here. We would have gotten a methyl shift, resulting in a tertiary carbocation, and then let me draw it this way. The water would have added to the wrong carbon, giving us this product. Okay, so we can see that the nucleophile is listed after the comma on the top of the arrow for this reaction. So in step 1, we have the mercuric acetate and the nucleophile, and the nucleophile can be an alcohol instead of water. Okay, we even have here ethylamine acting as a nucleophile. So if we had used that instead, what would we have gotten? So the overall reaction here, let's just draw that, is, or the general reaction is this. So we add our nucleophile to the more substituted side and hydrogen to the less substituted side. So if our nucleophile is ethanol, I'll just put A here, indicating that I'm doing part A. Our nucleophile is ethanol, so we have O, CH2, CH3, and I'll just leave the hydrogen out. And for B, we have ethylamine. So remember, in that second step, we're going to pull off a hydrogen, okay, after the nucleophile attacks, and so we're going to end up losing a hydrogen from here. Okay, so let's go ahead and draw that. So the nitrogen is what is acting as the nucleophile because it's got the lone pair instead of the oxygen, and this would be our product for this reaction. So we can see that other nucleophiles can work for this reaction as well. Alright, thanks for watching, and I need to pull that up a little bit, don't I? So we ended up with losing one of the hydrogens here from the ethylamine, and then we also had pulled a hydrogen off of that ethanol when we did that reaction. So we get the other part. Let me go ahead and draw that out so there won't be any confusion. Alright, so when ethanol is acting as a nucleophile, this is the part that we're adding as the nucleophile. And when ethylamine is acting as a nucleophile, that nitrogen has a lone pair. This is the part that we're adding, so we're losing one of those hydrogens. Okay? Alright, thanks for watching, and I'll see you in the next video.